Recording in progress.
Something's going on. Let's go to my settings. Anyone thinks they know how to troubleshoot, but I'm in settings. Let's see. Yeah, so my iPad is not wanting to share right now. So let's do this. Just gonna Google this real quick. iPad not sharing screen. Let's see. I'm on a Mac on my personal computer, but I'm using an iPad from ACC.
You are currently using the Zoom that we are talking now.
Oh, Mac. Oh yeah. So the one I'm talking on now is my computer, right?
Okay, so
every day I have this iPad, and this is how I share with you guys. So I share what's on the iPad when I'm writing on, and this is not working. So I'm just I restarted the Zoom app, but I'm going to, when I Googled it, it said restart your iPad as well, which after class I charge it, but
I couldn't hear you moment. So you just simply share your iPad screen with your Mac, so you can share your iPad screen with us over the Mac.
Right. So that's what I would love to do, but ACC blocks me from sharing this to my Mac. It doesn't work. I could have asked at the beginning of the semester, but instead I just log into Zoom on my iPad and I share through there. Or maybe I was in the right room. Yeah. That's good. Okay. Well, I'm joining again. Let's see if this works. If not, we'll go to plan X,
You can share the document.
Oh, this looks normal. Okay, this looks more normal than what I'm.
Okay, so you actually did have to restart it.
Oh, and look at that. See, so I did have to restart my iPad. So hey, hack for everyone. If your iPad's not sharing on Zoom, or maybe if there's any issues, I restarted Zoom and my iPad. So Zoom first, then I restarted the iPad. Who knows which one actually did it, right? Because we can't really tell, but
that's true.
I mean, you got to just try it all, right? Okay, cool. Well, now yeah. Now I've just got to pull up the chat so that I can see you and the chat and all of this. And okay. So today we're going to be talking about, last time we looked at polar coordinates and polar equations, and we saw that motivation was this spiral and how it's constantly changing, and how would you graph that in terms of X and Y? It would be really hard, because it would be a piecewise function of a bunch of little pieces of circles, right? Now, today we're going to mostly talk about circles, but we're also going to talk about the spirals that we saw before. So let me get this pen connected. And here we go. So today we're going to talk about the graphing polar equations by just plotting points. So basically we did discuss this last time, so this is kind of a reminder. A solution to a polar equation is an ordered pair r comma theta that satisfies the equation. And the graph of that is the graph of all solutions. So for some cases, there were 2 points, or maybe infinitely many points and you would connect it and it's a circle or whatever the case, right? So you would have these points that satisfy your equation, and this would be the graph. Very similar to x and y, right? It's just a different concept because it's the radius and it's an angle theta. So number one just says graph r equals cosine theta, three cosine theta. So this is important. 3 cosine theta. And by plotting points. Okay, so basically we can just take angles that we know cosine of, and we can just calculate the radius, right? So, or r, right? So this first one, so if I substitute 0, cosine of 0 is 1. So r would just be 3, right? Then pi over 6, now I'm looking there, cosine of that is root 3 over 2. Pi over 6 is 30. Yeah. So it would be 3 times root 3 over 2, right? Then pi over 4 would be 3 times root 2 over 2. And then 3 times 1/2, so 3/2. And then pi over 2 cosine is 0, so 3 times 0. Now I'm going to pause here because then we get to negatives. Or it's just kind of an extension of the angle, like in another quadrant. So they are going to repeat. So first we'll get what this means here is like, these are exact and the next one is approximate. So if we want to get like approximate, you would put this in your calculator, right? So 3 root 3 over 2 is about 2.6. 3 root 2 over 2 is about 2.1. 3 over 2 is exactly 1/2. We know that. And 3 times 0 is 0. So what we know about cosine, so all of these, so cosine is even, which means cosine of negative theta equals cosine of positive theta. If you remember this from way back when, right? Whenever this was. So because of that, we could think of it like these, positive, keep going around the circle, or we could think of it as these negative angles. And then we just have to take the answers for the positive. Well, okay, 0, I guess doesn't count, but the answer for the positive angles, and it's the same. It's exactly the same. So we can do that. So we know negative pi over 6 will be the same as cosine of pi over 6. So it'll be, 3 root 3 over 2, which is about 2.6. Pi over 4 will be 3 root 2 over 2, which was about 2.1. Negative pi over 3 will be the same as pi over 3, so 3/2, 1.5. And then negative pi over 2, again, 0, 3 times 0, so 0. Okay. So now we basically are making like a table, like an XY table, but it's R and theta. And now we can plot these points. Okay. So if I take each of these points that I've written here and I go to plot them, I know, well, okay, we're going to have to be approximate because R is like that radius. So if it's a decimal, okay, guesstimate, it's between these two lines, right? And we think of this as like radius 1, 2, 3, 4, like that. And then you have the angles labeled for you. So let's go ahead and plot all of these points. So the first one will be, and I'm looking, when I go to plot my points, I'm looking like this way, right? Or I guess maybe like theta is here and R is here, right? And okay, doesn't matter. Technically R comes first, right? But I'm looking at those rows because that'll help me to plot. So 3, 0 is the first one. So 3 and then 0 will just, the angle 0 is right. I mean, it's right here, right? 0 degrees, 0 radians, whichever you like. And then 2.6 pi over 6. So pi over 6 angle and 2.6, you could basically make it 2.5, like right in the middle of 2 and 3 there. Then 2.1 and pi over 4. Okay, barely past 2, maybe 2.1 pi over 4. Then 1.5 pi over 3. So 1.5 pi over 3. Then 0 pi over 2. Okay, 0 pi over 2 is right here, right? Because pi over 2 is this angle at the very top. And if my radius is 0, it's always in the center. It's the origin. So really the angle could be anything, and 0 is going to be in that middle. Okay, now I could keep going, right? And maybe I should. So here's my positive, and it looks like it makes half a circle. So my negative angles should do pretty much the same thing, right? So I get 0, 0 again, or 0 pi, negative pi over 2. Oh, I'm starting from the right, my bad. So maybe I should start 2.6 negative pi over 6. So this is negative pi over 6, and 2.6 was like here, right? 2.1 and negative pi over 4. Again, this is negative pi over 4, negative pi over 3, right? And you can see they wrote the positive ones up here too, so you can see which angle it corresponds to. And I got 2.1 negative pi over 4. Then I get 1.5 for negative pi over 3, and then 0. And again, I can kind of see, okay, that wasn't the best, but it looks pretty accurate. And the graph is a circle. So the graph is a circle that passes through the origin. It's not centered at the origin. It passes through the origin, right? And I can, just like with X and Y, I can connect these points, and any point on that circle, like these are the exact points we know. I mean, okay, we did decimals, but like we know how to find cosine of pi over 6, pi over 4, pi over 3, pi over 2. But if I wanted some radian or angle in between there, like 50 degrees or, like pi over 8 or something, we could do that, and it would be on this circle, and we could find that point, right? And then to find the center here, or we can find the center, and it's going to be on this middle line, and just between 0 and 3, right? So it's 1.5. So the center is at, well, okay, so first I'll say center lies, I think your book says it like this, lies on theta equals 0, because that's the center of our circle. That's like, we've broken it between the top and the bottom. That's how we plotted it as well. And the center is at 1.5 for R and 0 for theta, right? So remember, this is R theta. And the center, if we want to plot it, is like right there, right? So here's our center.
Is it because you know it's a circle? And you know it's going to be halfway between?
So yeah. So it's because of the symmetry. So because cosine is even, and if we had plotted this, like, okay, say we plotted the top half, right? Like these thetas, and say it gave us something, okay, I mean, say it gave us like here, right? And then then we plotted these thetas, right? And it gave us this other half here. Okay, then we know the center would lie on the middle, right? So, and I guess it may not, I don't want to say it will always give you a circle, but I kind of think that is true, unless there's something weird going on with like a squared or a square root or something like that. So yeah, so that's how we knew, like, because of the symmetry, the center's got to lie in that middle, which in this case happens to be, well, what I'm calling the x-axis, but really it's the polar axis. Okay, cool. And so we are really just talking about circles right now, but then we'll get into how it could be. So it will always be a circle, but we'll get into how it could be that spiral effect and how we can get a spiral after this. So for circles, and notice how my equation was 3 cosine theta, and I had a circle with center 1.50, right? So keeping this in mind, the 3 and the 1.5 totally related, right? And then the cosine and the 0 are related, because if this was sine, it may have been different. So let's take a look. So if what this is telling us, right, is that for R equal to A, This is not, so, okay, don't think of this point as 0, 0, but just think of this graph as your circle. And the center is at the pole. So they're talking about this center, just picture like this is the center and it could be anywhere. It doesn't necessarily need to be at 0, right? But they're just drawing it kind of this way, which is a little confusing. But any line from the center to your circle has a radius r, right? Which in this case is actually a. Okay, if r equals a, so maybe I should write a. And the radius is the absolute value of a, because we could have that a is, so maybe this would even be in absolute values, because we could have -3 or something, and the circle's just kind of rotated somewhere else, right? Now we get to, so this is just if r is a. Oh, and I guess this is actually saying there is no sine or cosine. So this would be centered at 0. But in the next pictures, they're not. So we'll say, for this, we'll say theta varies, because it can be anything. But in this case, r is constant. Because r just equals a. Okay. But the next one is r is a sine theta. Okay, so if we have a sine theta, and this is kind of the important part here, this means that our center of the circle will be on the y-axis. Okay, so we'd have center on pi over 2, which is, I'm thinking of it as the y-axis, right? And then the diameter is the absolute value of a. So this time, instead of the radius being a, with this sine or trig function involved, a ends up becoming the diameter, so 2 times the radius, right? So you can see here, if we go, okay, like I don't know where the center of this is. Oh, did they do it exact? Is it 1, 2, 3, 4? Okay, so it's exactly like here, right? So this point is, so this angle is pi over 2, right? This angle, like the angle to go up there. That's our angle. And the diameter is a, so a is this whole distance, okay? Now, keep in mind, this graph here is a is positive. And if we want to see, what happens when a is negative, 1, 2, 3, I think I'll try to draw this as accurately as possible, but it's just a circle below. Okay, that doesn't look so good, but you get the picture, hopefully. So it's still centered at, like, it's negative. The center is now at negative pi over 2, and the diameter is still a, right? So, okay, I mean, that'll be the last one I draw, but so this is what happens when a is negative. And again, the center is still here, and this whole thing is still a. Well, this would be the absolute value of a in this case. And so the radius for ones like this is a over 2. And then the last one we have, r equals a cosine theta, right? This is going to be kind of like what we just, or exactly like what we just graphed. So you can see, let's see, that it's the same thing as sine, but just kind of at a different angle or using a different axis. So theta equals 0 is our center. Diameter is still a, so this whole distance is a. And this is if a is positive, right? And if a is negative, let's see, this. Oops,
If A is negative, it will look something like this, right? It'll go out here. And this would be A negative. And again, this middle distance is the absolute value of A. The center is still in that, is still A over 2. So center, or okay, maybe I shouldn't say center because radius, right? Radius is A over 2.
Which is where the center is, but okay. And notice how this, in this case, when it's like for both the negatives, the center angle is negative pi over 2. And here the center angle is negative, or is pi. Center theta equals pi. Or you could say negative pi, but they're both the same thing. I mean, it's related to 0 as well. So now we're going to see like maybe a few different examples of this before we go into spirals. Okay. So this example here, number 2, or has a bunch of parts, right? And the first one says graph -4 cosine theta. So we know the negative, like right off the bat, I can tell a lot of things. This negative means that it's going to go to the left, right? So it's going to graph to the left of the origin, right? And then I also know that cosine means, well, that's what, okay, cosine also tells me left because cosine is left or right and the negative is left, right? So if it was sine, it would be up or down. The circle from the origin, it would go up or it would go down. So these two things tell me that when we graph this, the circle should be on the origin to the left, right? And for this, I'm going to say a little note, no need to plot like precise points here. I don't know what the homework asks of you, but it should be very clear, hopefully. And if it's a crazy, weird graphing things, let me know. Because I know I have a list of 2 or 3 homeworks that we're going to be like dropping for everyone because they were chaos, right? So we can add one to the list, or I mean, work on it, right? Try it, but just let me know because I know Alex can be a little funky. Okay, so to graph this, okay, so I know a point's going to be here, and then -4 tells me. So I know this is like -1, -2, -3, and technically, okay, these aren't negative; they're still the same, but it just tells me the direction to go. So I know that my graph is going to have a point here as well. And yes, you could try to find a point in between, but I'm also okay if you just kind of, oh gosh, you just try your best to graph a circle, right? Something like this. And this is our graph. So these ones are not too bad so far. Right? Then the next one says R5, so 5 sine theta. So this tells me this is positive and it's sine. So this tells me up. It should be, okay, I should say graph is up from the origin. Or above, you could say, I guess, but too late. I wrote up, right? And then it has a radius, or it has not a radius, it has a diameter. So another thing was in this previous one, like diameter was equal to 4. That's how I knew the point at 0 should be 4 away, right? And this next one, diameter equals what, 5, right? So I know 0, it's going to start, that's going to be a point on the circle. Then it's going to go up 5. 1, 2, 3, 4, 5. Oh, that's all the way to the top. Okay. And then again, if you wanted to get 1 or 2 points, totally fine. but you do not need to because we just know it's going to be a circle. So even on your homework, you should be able to just get these 2 points on the end and say, like, there's that nice graph feature that works sometimes, right? And you can like connect them and it will automatically make a nice circle, right? And I know there's a way to do that on my iPad, but clearly with the issues we've already had, I'm going to scrap that right now. I don't know how to force it to work. But yeah, so in this case, we have our circle here, and that's r equals 5 sine theta. And then our last one is negative sine theta. Okay, this is going to be, well, just tricky for me because it's tiny. But so the last one, this is negative sine theta. This tells me the graph is down from the origin, right? And the diameter, ooh, this is small, is 1. So the radius is a half. So this means I'm going to get the point at the center. I'm going to get the point at 1 down, right? And then I'm just drawing a teeny tiny circle from there, which maybe it was easier to draw smaller than a bigger one. But this is my graph, and that's r equals negative sine theta. So these are kind of, it seems, well, it is simple. So think of it like it is simple. This is what they are, right? If it's sine, if it's cosine, you can figure that out. If it's just r equals 5, I mean, this is a circle, right? It's centered at the origin with radius 5, right? Or something, whatever, something like that, right? So rarely will you get that, most likely, especially like, well, on the test. I think it'll be more like, you know, any one of these really, where we have any of these, right? A positive or negative, sine or cosine, and a number. Okay, in a real world situation, should the polar coordinate system we use to graph the instance, like negative 4 cosine versus 5 sine, be mutable? No, it's much more complicated theory. I'm not sure what you mean by mutable. And maybe that's because I'm not good with vocabulary. But if anyone thinks, so there's a question in the chat, and okay, we can, yeah, if there's time, you can ask later or unmute and maybe talk more about what you mean, and we can come back to this, right? But okay, cool. All right, so circles are cool. They're nice, they're even, they're symmetric, they're pretty, they're fun, right? If you think that's all true, well, here's something that maybe is even better, or maybe if you don't like circles, you will like spirals. So now we're going to talk about spirals, and spirals are just circles that are changing, like circles that are connected that are changing, or at least that's how I'm thinking of them, right? Now there's 2 different types of spirals. One is going to be this Archimedean spiral, and the other is going to be a logarithmic spiral. Okay, now notice Archimedean, it just is r equals a theta. Very simple, like no trig is involved here. This is how we get spirals, because trig makes it even and gets us back to a circle, mostly because sine squared plus cosine squared equals 1 and x squared plus y squared equals 1 is a circle. So like there's something behind the scenes that's related to that. But the spirals, if we take the trig function out and we just say r equals 5 theta or r equals a theta, right? Then what's happening here is as theta changes, the radius is also changing, because theta is not symmetric. Like cosine of theta is symmetric because it's, cosine and sine, they're these waves that are perfectly symmetric. But if I just graphed theta just by itself and I said, okay, what does that look like? Well, it looks like this. It's a line that's just changing all the time, right? So when we look at this, our spiral, where our circle, the radius is constantly changing based on theta, and vice versa. The theta is changing based on the radius, right? Okay. So, and then notice with logarithmic, okay, let's hope this makes sense to us. It's r equals e to the a theta. Okay, like here's an exponential. So logs x, like e. I always think natural logs. So ln, this makes sense. Now in this first one, which it should, or maybe it's just a pre-example because it's not numbered, but we see 0 is less than theta. So they give us this domain restriction, right? 0 is less than theta is less than 10 pi. And the reason they do this, probably, I'm assuming, is because you could technically, go on forever here. Your radius could go to infinity, and so could theta. Theta could go to infinity, but technically, right, like 45 degrees is the same thing as 360 plus 45 degrees, right? Which is the same thing as another 360 and another. So even though that number is going to infinity, the angles are actually in the same directions, but the radius is changing. So the point is in a different place, right? So, and it's kind of like saying, or like I'm thinking of it this way for some reason, like if you are jumping like into a pool or off of a board and you're like, oh, I did like a 360, right? Like a full spin. You're facing the same way as if you just jumped straight. So I could be like, so did I, like I did a 360, but really it was 0 degrees, right? So like, that's not really accurate maybe, but you're facing the same direction. So if somebody blinked and didn't see you spin and you're landing the same way you jumped off, they might not believe you, and now in today's day, you can record it and it's all there. You can pause it and be embarrassed by it. Right. But this type of thing, I think that's what I think of at least. And how I think, well, how is this changing? What does this look like? Well, if I'm facing 90 degrees, that's the same thing as if I am turning around and still facing that way. Okay.
Mm-hmm.
But let's take a look. At, the first example is graphed forest, and you can see, it's actually probably really hard to see, but if you start at 0, every time that you get back to 0, this is a full rotation. So, okay, what is that? 2 pi or 360, or at least, so it said up to 10 pi. So you're at 0, then like 2 pi, I'm seeing 3 pi, and I guess it's the second time you get to 0, 2 pi, 4 pi, because I'm counting by twos. Then like 6 pi would be here where I'm circling. Maybe I shouldn't have chosen blue. Then 8 pi. Then I go around one more time, and 10 pi. So each time I do a full circle, even though my radius is different, I counted by 2 pi, right? I did 2 pi, 4 pi, 6 pi. And that's, and notice here, this is consistent spacing. They did this with we did this with like a computer, right? But this is consistent spacing, and you'll always start in these cases, and keep in mind, this is 0.1 theta, so very tiny of an A value. So you'll always start at theta equals 0, and then going to the right. So I'll draw that as well. So you'll always start at theta equals 0 and then go to the right. When we graph these, you'll notice that's kind of just the pattern of how all of them are. And you just have to be consistent with it. Like, if we chose the other way, okay, it would be fine, but it's like reversing the orientation. And then this next one, so notice R equals e to the 0.1 theta. So A is the same, but this is a logarithmic. Look how different it looks. So we start again, I think they're starting at the center sort of. They go 2 pi, 4 pi, 6 pi, 8 pi goes crazy. And then this kind of looks like, what are those like hermit crabs or something? This looks more like that type of shell where it's like not so even. So here I would say the spacing increases with each like 2 pi, with each revolution. Right? So the spacing, just as theta gets bigger, the spacing here is getting bigger and bigger. Whereas before, with R equal to just 0.1 theta, the spacing is equal at every 2 pi or every pi rotation. And then they ask us to do this example. Okay, let's try to check out how we can actually do this, because you do have to plot a few points, and then you just kind of connect your spiral and hope for the best, right? And it'll look almost the same. Like we should all, you can compare yours to mine, but they should look pretty much the same. So if I want to graph r equals 0.4 theta. So, okay. So I know I start at theta equals 0, right? So, I mean, okay, I know that. But then theta, I want to go, I'm still in this. So I want to go 2 pi. I mean, I think, maybe I only did up to 4 pi or something, but we'll start with 2 pi and see what one revolution, where that takes us. So if theta is 2 pi, then r equals 0.4 times 2 pi, right? Which equals 0.8 times pi, which is, I mean, approximately 2.5. So here we do kind of need some decimals, right? Now, I think I tried to go 4 pi, but it was too big. So like when I calculated, so then I just went 3 pi and then I ended up doing pi as well, just to get a few more points in here. But so you can either do like 2 pi, 4 pi, 6 pi, and then like kind of graph it based on that, like spiral based on those points. Or you can, I think in this case, what they're doing or what your book does is it actually does, and I did this in the wrong order, right? It does 0 pi, 2 pi, 3 pi, and then if you could fit it, 4 pi, because then I'm just showing you this. If you know those points, like 0 would be here. Then if pi was over here, you know that it's going like this. Then if 2 pi was here, you know it's there. Then 3 pi, then 4 pi, and it would be like a spiral, right? So this is the idea if we get these points, okay? Now it's really hard to see in these two above because they're so close together, but we didn't, we were just observing that. So now let me actually try to figure this out. So I'm gonna keep going with pi and 3 pi. So then r would be 0.4 times pi. And you want to get this decimal so you're able to graph it, right? And 0.4 times 3 pi, which is approximately, this one was, I think, 1.25. And this one, I'm getting 3.8 or something.
3.8.
3.8-ish or 3.75 or something. But okay.
3.77.
Or 7.7. Okay, maybe let's stick to 2 decimal places. Okay. So something like this, right? So here we are. And now I want to graph all of my points. So I'm going to pick a nicer color. Maybe like this. Okay. So I'm going to start at 0 here. Then I'm going to plot I'll plot pi 1.25. So pi is, remember, with these angles, this is 0, pi over 2, pi, 3 pi over 2, and 2 pi, right? And then you could keep going and say 2 pi, then 3 pi, then 4 pi, right? So you could just keep going around and around. So for pi, I'm at 1.25. So I'm like, right here, about, right? For 2 pi, I'm at 2.5. So 2.5, that was easy, or better. And then for 3 pi, I'm at 3.77. So 3 pi is again over on this side, and I'm at 1, 2, 3. I'm counting these, 1, 2, 3. This is 4, so make it really close to 4 because, it's like 3.7 something, right? So, and then I could have done 4 pi, but I think it goes beyond. At least I think it goes like just at 5 or beyond this. So that's why I maybe left it off. But now you remember you start at 0, 0, right? And you always go to the right. So we're going to go up to the right, down through the first point, then around through the second. Okay, my spiral is not the best, then down and around. And then, okay, so some point over here, I don't exactly know. Maybe this wasn't so nice, right? And you loop it and keep spiraling, right? And if they extended more, maybe I could have done 4 pi as well, but I think I was also maybe being lazy. I think at least like 3 or 4 points is going to help you get this spiral going, right? Now, another place to see this, which is pretty cool, is Desmos. So maybe later,
or actually there is a graphing calculator exercise at the end of this well, I don't have it available on my phone, but I can do it maybe on Desmos on my laptop.
Yeah,
Okay.
it should be pretty easy.
Yeah, I should be able to share that, assuming we don't have any laptop crises. So now looking at if we want, okay, this was the fun spirals. We are going to talk briefly about lines, and then we'll do the fun graphing things with spirals and what happens with this. And it's similar to circles. Like it is very cut and dry. Like unlike before when we learn things and it's like, oh, well, you can do it this way or this or this or this. This is just kind of the spiral is the way it is. It starts at the center. You figure out a few points and it spirals. Same with the circle. You figure out the top half or the right half or the left half, and then you figure out the other half. And they're pretty cut and dry, I would say. But now we have lines that we can graph, and it's like, okay, I know how to graph a vertical line or a horizontal line by saying like x equals 5 or y equals 2, right? But how do I do that with r and theta, and what do lines look like? I mean, whether they're vertical, horizontal, or even diagonal, right? So we didn't really look at that yet, I don't think. Okay. So what we can see here is that they break this up into a few things for us. So first they talk about the axes. Theta is 0 is the x-axis. Theta is pi over 2 is the y-axis, right? So they talk about that here. And basically, so this is theta equals 0. This is theta is pi over 2, right? And in this case, r is positive. Same thing with this case, r is positive. And in this case, r is negative. This case, r is negative, right? So that's how we know where we're at when we graph. Then a line through the origin. So those are just your standard like horizontal, vertical lines, the axes. A line through the origin, theta is A. So theta was okay. Not really sure why this keeps happening, but here we are. Can you guys hear me? Hopefully.
Yeah.
Okay. All right. Well, we'll let my computer just be horrible still. Okay. I will rejoin Zoom maybe on the next once we finish this section. So we can see here. Here's an angle in we draw it in standard position. So whatever the angle is, we draw it in standard position, and then we just do an entire straight line through the origin. Now, if we want horizontal or vertical lines, right? So horizontal, the y is a and r is a over sine or a. We did see this, I believe, yesterday, Tuesday. And for vertical lines, r is a over cosine or a secant. We saw it, but we didn't like point it out, right? So in this case, you can see like here, a is 1 and here a is 2. And I'm just getting that from these equations, right? So this here.
This is like converting the polar equation to like a rectangular, right?
Yes,
so because
exactly.
r sine theta is just y.
Exactly. So this is like y equals 1, and this is like x equals 2. So these ones are, we did talk about these last class, and these are, I mean, the same, like virtually the same thing, right? So like looking at number 4, we did talk about this last class, and we can see here what this tells us is this 5 means that, and sine theta, I mean, okay, that tells us it's this.
So this is like y equals 5. And if I was to graph this, I would just go 1, 2, 3, 4, 5. I would go up 5 on the y, or, I mean, okay, you could just graph literally the line y equals 5, or you could think of it as if sine of pi over 2, that's 1. So 5 at 5 pi over 2 is the point, like this point that I just graphed is 5 pi over 2, right? For r theta, right? Or it's 5, 0, or 0, 5 for x and y, right? And this is it. That's just the line for that problem. Let me see.
So you actually draw that line.
Oh yeah. So you draw this line. So it says to graph it. This is the graph. Yeah. Oh shoot. And I am back. Here, give me a moment, guys. I'm gonna leave audio on Zoom. Let's see. Okay, so I should be back. And we are recording still. Yeah, so this is going to be annoying because it's like going to be broken into so many recordings, but that's okay. And I'm still sharing, so that's great. Okay. Okay, so let's just take a look at this last, or the last few examples before the fun graphing things. So that one was, I mean, okay, in my opinion, a bit boring because it's just a line, right? But this one is, oh, well, same thing, just a line, actually. I think it's, do they finally get exciting? I don't know. Maybe these are all lines. I'm not sure. So, well, I guess they are all lines and they're just horizontal and vertical, but for some reason we haven't done, I don't know if any of these are there, but we'll see. So if I have r equals -2 secant theta, I don't know right away what that's going to be, but I do know this helps me so much rewriting it in terms of sine or cosine, because then I see cosine and I'm like, oh, that's x. It's going to be a vertical line, right? And I see -2. So this tells me it's the same thing as x equals -2. So I can do this and graph a straight line. Granted, it's harder to draw a straight line when circles are your graph. But here's our line, and this is just a vertical line, right? And maybe I should have written up here that this one was horizontal. Oh, and now this is just asking, okay, so we don't have to graph all of these. Number 6, each of these pieces are just asking, do we have a circle or a line? And you should be able to tell sort of quickly, because, well, keep in mind up here, these are your hints that like it's a line through, well, okay, those are axes, but these are your hints that they're lines. And then as we went over above, which maybe I don't want to scroll too far up, but those would be the circles. So this first one is 3 sine theta. So because it's just sine theta, and it's not in the denominator here, I know this is going to be our circle. This is like what we did at the beginning of class. So this is going to be a circle, and it just has diameter 3. I mean, you don't need to write. It's really just asking circle or line, right? But diameter is 3, and it's also, I know because of sine, it's going up. So if I did want to graph it, it's like something like this, right? Okay. Now this next one, so r sine theta equals 3. If you remember your formulas, this one's really easy because r sine theta is x, right? So you know this is just a line. Or wait, it's y. Oh my goodness. All right. If you know better than me, no. So this is just y. So right, this is the line y equals 3. And I mean, okay, I won't graph all of these because hopefully you can. If you'd like to see the graph, let me know. Now this next one, so this looks really different. However, watch what I'm going to do. 3 cosecant is 3 over sine theta. And you could either use above, or you could say, oh, if I did multiply both sides by sine, this is exactly the same as part B, but it looks very different, right? So you really have to kind of
be aware or change it to sine and cosine, or, you do have to remember some of these things, but it looks the same. Like this looks good. So this is also a line, and it's the line y equals 3, right? Same, same as B. Now part D, okay, this says R cosecant equals 3. So this is R over sine theta equals 3 again. But this one, it also looks to me like, oh, it's probably gonna be a line again. But if I multiply both sides by sine, I get R equals 3 sine theta. And now this is exactly the same as part A. So this is going to be a circle. Same as A. So they're definitely trying to trick you here, which I don't know why, but I guess it's good. It's good to recognize this, right? And if you don't, it's good to see this so that you will recognize it. Because a line and a circle are not the same thing, right? So if you're guessing wrong, I mean, you got a 50-50 shot, I guess. But so part E is saying -4 secant. And again, you might know right off the bat, but I really like to just change this to -4 over cosine. And then I do see it that cosine, like you could multiply by cosine as well, because this is the same as R cosine theta equals -4. And this is X, right? Now it's finally X. So this is a line, and it's the line X equals -4. And then it looks like they just messed with this one as well. I mean, this one here, I see a circle, -4 cosine theta. They're not fooling me there. And this is a circle with diameter 4, but to the left, right? So if you wanted to graph this, I mean, diameter 4, and it's to the left of the origin. And then R secant, R over cosine theta equals -4. So, I feel like we've done this one. Or, okay, I guess they're just writing these. They're all very similar, right? But they're writing them in different ways. I'm like, didn't they already write this one? But they didn't. They wrote it differently, like -4 secant or something, whatever it was. But so now this one, it may help again. Oh, this is the same as F, right? Because it's -4 cosine theta. So this is also a circle. It's the same as part F. But again, they just look so different. So it's really easy to mix these up. So that's what you want to be the most careful of here. And this last one, R cosine theta, I mean, I know that's X, right? So this is a line. Or you could divide by cosine. And if you did that, it would look exactly like this guy here. And you'd say, oh, this is a line, right? Okay. So that's the whole fun of circles and lines and polar coordinates and polar equations. Now here, okay, so these are the instructions that you have, right? I think you can also do this on like a graphing utility, a graphing calculator, I'm pretty sure. However, well, I did find mine recently, but it is dead. So, of course that's helpful. But I think it's going to be best if we follow these directions, right? And go to Desmos, check it out, do the grid, and then, oh, wow, there's some crazy mode things we have to do. Oh yeah, because you have to change from a function to polar coordinates. And then we'll be able to graph this and see which one it actually looks like. Because notice how this is a transformation. Like we've been just looking at 4 cosine theta, and that's like a circle. But as soon as you add in a number here or a number here, it's transitioned and it looks like one of these 4, which is kind of exciting. And to maybe find the one that looks the prettiest, like I don't know what that equation is, but I mean, I'm sure you could just Google it, but that would be cool too.
So let me stop sharing this real quick. How do I, okay, done. Let me make some saves. I will post these notes. I probably won't write anything about the Desmos because this is not, the Desmos stuff is not going to be on the test. So we're actually ending quite early tonight. Well, we'll play around with this. Let me, okay, how do I, okay, Zoom, stop sharing. Okay, so now we're back here. Just having a good old time.
Oh, is there a way to do that? What do we call that, stenograph or whatever that was on the beginning of the?
Yeah, so
Is there an
okay,
what is the equation for that?
yeah, so that's such a good question. Because right now I just don't know. I'm not prepared enough, I guess.
'Cause I tried to figure it out. I couldn't get it.
Yeah. So I bet we could look this up. Let me see.
But anyway, we can maybe get there. A spirograph, that's what they call it. Because you'd have to say it doesn't include the middle or
Yeah,
something.
it's
Or maybe it's just not shown.
you need like a lot. I think you need like a lot of points going on, but okay, let's first go to Desmos. Yeah, we'll first go to Desmos and let me try to follow along. Because I did this last week, but of course, let's see. Okay, so I have to share my screen. I assume they're ovals. Oh, this one, yeah, they're like oval looking. Let's see. So here, share. Okay. Okay, so here I am. Well, and now I won't have the chat. This was bad. Okay, that's okay. So we're on Desmos. Click the graphing calculator. Got it. Go to tools, which okay, now I can't see because Zoom is in my way.
The settings, the little gear. I mean, it's a wrench rather.
Yeah, that's why I called it tools, but who knows? Okay, grid. So you want this guy. Whoa. And then type your equation in R and theta by spelling out theta. Oh, I for some reason thought.
No, there's a theta symbol in the alpha keyboard.
Oh yeah, that's why. Okay. So that shouldn't be a problem. So if we want R equals 1 plus 4 cosine 4.
Does it actually?
Oh, okay. You can type theta and it changes. That's pretty wicked.
That's kind of cool.
Yeah. Okay. So what? Oh, whoa. All right. Here we are. But wait, did I change? Okay. I guess I changed everything, or maybe it assumes. I think I thought I had to change to polar coordinates, but you know what? Desmos might be fancy enough that by now, because these directions could have been made 5 years ago, and now it's like fancy enough. You don't have to change anything. Because look. Okay. So it looked like in these. Okay. It was A. It was A, right? Now you could mess around and see like what happens when I do minus. Like, okay, it looks a little bit like A, but things have swapped, right? The big side has swapped with the little side, like flower part. And then what if I do, I don't know, like, oh wow, nothing in here, 0.5. Like, oh, like totally crazy. So you could mess around with this. Now I did Google or like spirograph. Formulas. Okay. Yeah, like this looks, well, this is maybe, okay, so it might be true that spirograph's formulas are way too complicated just for what we're doing, which is probably why we haven't graphed it. Because it looks, unless, oh no, that's not really. Yeah, it looks like to get like this whole, to get this cool looking thing, I think you need like this. You need parametric equations with polar coordinates potentially.
Okay.
We're using T, it looks like, or instead of theta, or alpha instead of theta. I don't know. But yeah, so I mean, this is an example. And I can, if I find anything, I can send it. But this is pretty cool to play around with too, even just to say, oh, what if wait, that's 0. What if I don't mess with that? Or what if I keep that and I don't have a number here? Oh, it's just a simple flower, like 3. What if I have, whoa, what if, okay, that's a really big number. But like, what if I have 2, 3 plus this, 2 plus this?
Like, so it changes, I mean, what's going on, right? You can probably find a pattern in it too. And what if I change this to sign? Like, what does that change, right? This one, so if you look at your notes, part C looks like it would be sign, right? Now, okay, I changed all the numbers at this point, but part C looks like if I did 1 + 4 sine of 4 theta, well, okay, maybe it's not plus even, but it looks something like with sine, right? Oh, maybe it's minus. There we go. I think that
There you
looks
go.
like part C. Yeah, so we figured out A and C. Now, really, B and B, I'm not totally sure. It must be something to do with like not having as much in here, or maybe like, yeah. I'm not sure. Or could you have a negative in there? Oh no, that just flips it. Yeah, I don't know, but pretty neat.
How about a
Hmm.
logarithmic one?
Oh, right. Okay. Let's see. Well, okay, so this is like R equals E to the what do we say? Like 0.4 theta, something like this. But this is a spiral. These were spirals. Okay, so that was to I think 0.1 might be better. So
There you
these
go.
were back to the spirals, and they're getting like, notice how this is small, but then here to here it basically almost doubles, and then 4 to here, and then it just gets huge. And you could zoom out, right? And like it's, well, oh, they stopped it. Okay. Oh, because it's 0 to 12 pi. So you could change this to even be like 30 pi. Well, why my P is stuck on my, yeah. And you could change 30 pi and then it keeps going even more, right? So that's pretty cool. And now, I mean, now that's very zoomed out. We're at like thousands here. But anyway, so yeah, so this is something fun to play around with, not on your test, not going to be tested, so don't stress, but you do need to know, this general idea of spirals and how lines work in polar coordinates, how circles work in polar coordinates, just this idea that we've discussed today, right? So this is what you need to know. And I'll stop sharing for a second. Oh, yeah, okay. So here's, let's lay out what's going on with the rest of our lives here, right? So today, so we just finished 8.2. If the homework is really hard, I can't remember. I think I extended it to be due Tuesday evening. So come to class next Tuesday. If for some reason you like really can't get one of them, because I feel like we didn't do very much. So I'm not sure how hard the homework is going to be. But hopefully it's similar to what we did do. I just didn't get a chance to look at 8.2 homework. So give it a try this, by next Tuesday or this weekend, and come to class with some questions or just, if you want to like, whatever you want to ask, right? And then I did post those reviews. We will go over, did I post the answers? That's the question.
That's a good question.
Yeah, so let me look now. I'm
You
gonna
usually
post
give the answers to the book
problems. So yeah, so I'm gonna post, let's see.
Can I ask you a question about the book problems?
Yeah.
So it looks like this is actually set up for more of a full semester type of final
Oh
exam.
shoot, is it? Okay, this is not true.
Okay, yeah, because like half of it is about the
Old
most
stuff?
recent sections or whatever, but then there's about half of it that covers the rest of the semester. I think.
Okay.
I don't know. I kind of just glanced at
No,
it.
it probably does, and it's probably because because we want, ideally we would give a final that is cumulative, right? And if this class was in person, I think it would be a lot different. And I think also sometimes with calc and pre-calc, they add an extra lab, and that means you meet an extra time a week, and it would be, I don't want to say like it wouldn't be more intense. It would just be even more material. And I think the final would then cover everything, like typically. So our final, I mean, I don't know I wonder if I made up the fact that it's not cumulative, but I'm pretty sure another professor that coordinates the course just told me, oh yeah, the last final is just the last unit you did. But I think in the past, like those book problems that are review, we've used these from previous semesters. And I think in the past it has been cumulative. So that is a good point to make, that like, do not, good review, right? But do not stress about anything that was prior to our, unless you see it in the practice problems, then that means it's on the final, but I'm pretty sure I stuck to like this material.
Okay.
So
That's cool. So don't worry about doing all this stuff.
Yeah. Do not and again, the book review, it's like insanely extensive, right? Like you do not need to do every book problem. Like that's, if you have time, great. But I think it just gives a lot of extra practice just for people who want to do more problems, right? So I will post, I don't see it here. So let me.
Like it talks about the vectors, like work, calculating work and stuff like that.
Well, I want to say, I wonder if work is on there. Let me open up the practice real quick. Because I do wonder, maybe we threw in some things that we didn't, because didn't I not include some stuff on the previous exam? Or
that's a good question.
Yeah, I want to say that might be true. That whatever I like didn't include on the previous exam might be on this one.
Okay.
Conic. So I see conics are on here, polar equations. Like throwing a ball. I don't know, parametric equations. I think. Let's see. Oh yeah. So there is. So if you and maybe that review is true to everything, but there is like amplitude, period, and phase shift, like just finding that. And then solving. I don't know when we did that, like solving an equation that's like sine squared x minus cosine equals something. But this, and I'm looking, I could share, I guess. I'm looking at just the practice test, but that I posted. Oh, not chat. Share again. So I'm looking at this. And this is the practice problems that I've posted. So this is what we will do next Tuesday. I do hope, I'm guessing we'll have enough time. And you'll see, I did try to not put too much. But like here, I also put type of conic based on equation, right in standard form. I don't have an example of this, like other than what we've done already. And I didn't have time to like write another one that worked out, because some of these are hard to like just change the numbers or write a different problem. Some of the ones in your textbook, like I don't love all the time, or they're like a little too hard. So I added that just so you guys know, like there's going to be a question like this, right? But the one that you're talking about the work, and I feel like I left this off on the previous test, and that's why it's here, is this one. Like a child pulls a cart with a force of 10 pounds. So this is like on the previous unit, right?
Okay, yeah.
But there's going to be one question on the final. So I guess technically this is just the last unit, but then it's like a little stuff that I kind of didn't put in the exam.
I was looking at the book problems, but yeah, that's fine. Yeah.
So it's in here too. So whatever's in here, like, and even this stuff, this is definitely on the exam. So if you see book problems that are similar to these, I would say go for it, right? Okay. Otherwise, if you see like stuff from way back when, or I don't know, I haven't looked over these, then it's not going to be that. But I will say, is the practice test a review? So McKenna, there's 2 reviews posted on Blackboard. One of them is the practice test, or the test for practice problems. And the other is the book review problem. So there's 2 reviews, and they're both called test 4, like test 4 final book review problems, and then test 4 practice problems. So I hope that answers your question. So there's 2 lots to review. Now I will look, I need to find the book answers. I know I like have them on a spreadsheet somewhere. So let me see. Test 4. Yeah, they've got to be somewhere. Oh yeah, final exam review key. Okay, so I'm going to post the book problem answers. Now, granted, it doesn't show all the work, right? But at least you'll have the answers over the weekend if you're studying and reviewing. But then, and then on Tuesday, we will go over those practice problems, and hopefully I can answer any other lingering questions or anything like that. And then your exam is Thursday, normal class time. right? So so it's kind of like next week is our last like week of class, I guess, right?
Oh yeah, right. After we're done with the test, that's it, right?
Right. Yeah. I mean, hey, you can show up to the link the following week, but I'm not going to be there. I'll tell you that. I'll get an email. They do well, and I realized after like learning a lot about. I mean, I thought I already knew Zoom, but I learned a lot because they like there is a way, and somehow it got turned on that you can get notifications like anytime people are in the Zoom, or you get a report of like all the people that have joined at exactly what time, exactly how long they stayed. So I knew I could have this, right? But I never knew it was so intense. Like it'll tell me, you know, like even when I get kicked out of the class, it tells me like I left, and then it says I came back 10 minutes later and stayed for 30 minutes. Like it's
Yeah.
very
Well,
bizarre.
we're not good if you leave, but yeah.
Yeah.
Good to
Right.
know.
Yeah, good, right. I mean, hey, good to know for all of you guys, because then, yeah, if somebody tried to say, "Oh, I was there for 2 hours," Zoom tells me otherwise, you know. And for those of you that attendance purposes, if I ever mark you absent or incorrectly, feel free to let me know because then I can go check Zoom and it will be there because that could just be an honest mistake. I'm not trying to mess with you, but I do like I see the answers for our question of the day, right? But then I also go into the Zoom report and I just see, okay, who was in class, and a few people, sometimes they come late or leave early and that's fine. But I check that so that like I can mark them present, because if they were there, that makes sense. So some of you sometimes get worried, like I didn't answer a question, but I still see that you were here, so don't worry. And yeah, German and Joseph are celebrating. Maybe just wait 1 week from now. Maybe.
Right.
But yeah, so and it'll be the same as all the other tests. I'll post it to Blackboard. You will, set everyone's camera needs to be on. You'll set up, whether you set it up with your phone or what, just make sure your devices are charged. And then you'll like type done in the chat when you're done and you'll submit it however you submit normally. So it'll be exactly the same. Don't panic. It's, just think of it as just another test and all the same thing.
Okay.
But yeah. So that's it for tonight. I mean, I'll stick around a few minutes if people have questions or anything. But otherwise, you get off a little early tonight. Which is
Are you going to
good.
do a question of the day today?
Oh shoot! Question of the day. Oh my gosh! Okay. Let's see. Oh, well, okay. This maybe isn't a great question because it may not apply to everyone. But maybe for those of you that maybe celebrate Hanukkah or something else, you can let me know. But I'm doing a Christmas question. But so if you celebrate Christmas, or if you did as a child, or if you ever did, what would you leave for Santa? That is what I want to know. Like what type of cookie, or would you leave carrots for the reindeer, or what would you do? And I can tell you, I guess, what I would do. So as a kid, and if you celebrate like Hanukkah or something else, like what is you can give me some tradition that you would do, right? And yeah, okay. And poor David never got to believe in the spirit there. But yeah, I would. Yeah, and William always tried to catch him. That's funny. We would always leave carrots for the reindeer, and like I was so convinced. Like I was more convinced that reindeer were there and Santa didn't come. You know what I mean? And I was like, Mom and Dad just eat the cookies after we go to bed, and the reindeer get the carrots though. But we would leave, yeah, like chocolate chip cookies or something pretty basic, probably. But yeah. Yeah. And Michelle's like totally love carrots. Yeah.
Yeah.
And then, for those parents that were like, oh, we have to leave juice or no milk because Santa's allergic. Like, I mean, I don't know if parents actually do that. They like can't have dairy or something.
Santa needs to lose weight.
Yeah.
So
Santa's on a
fat-free.
this year. Yeah. Yeah, right. Gluten-free, like dairy-free, I'm sure families are like that now. I mean, when I was a kid, definitely not. But yeah, feed them. Yeah. Meanwhile, like my dog ate the carrots or something. I don't know. Yeah. And Michelle said 1 year her dad told her to leave whiskey. That's great. Yeah, I feel
yeah, because it's really for the parents.
Of course.
Recording stopped.
Yeah. So that's really funny. But yeah, so thank you guys. So go ahead and put your answer, in the chat there. And